for now, we've got someone that I think I can call my friend. Stefan, are you around here? I'm paging Stefan to the stage. There he is. So last time we spoke, Stefan, you were threatening to open source, or the last time you were on here, I guess, and even the last time that you came onto the MLOps community podcast, you were threatening to open source Hamilton. And since then, you open sourced it. So we want to hear what is up now. What have the updates been? How's it been going? I'm excited to hear. It's been almost like a half year or maybe a year since we last heard from you about Hamilton. So I'm going to hand it over to you, man.
Cool. Thanks for having me, Dimitris. Yeah, definitely. Hopefully I'll answer those questions in this talk. So my name's Stefan Krawczyk, and I lead the model lifecycle team at Stitch Fix. And I'm going to talk to you today about Hamilton, a micro framework for creating data frames, and how we use it at Stitch Fix. So what to keep in mind for the next 30 minutes or so is, one, I'm going to try to convince you that Hamilton is a new paradigm to create, data frames, but not only that. The second is that it's a productivity boost for teams. Hopefully, I'll give you enough motivation to show that. And then the third thing, it is open source, and you can look at all the code, and we do have a community on Discord. So outline. I'm going to start with the backstory. So how did Hamilton come about? Well, there was a data science team named the Forecasting, Estimation, Demand team. They're a team of data scientists responsible for operational forecasts that the business makes decisions on. So for instance, what should our staffing level be at a warehouse? It's also one of the oldest teams at Stitch Fix, so their code base has been around a while. Their workflow to create forecasts looks something like the following. They get actuals, so marketing spend, signups, create a featurized data frame from it, fit some time series models, predict the future, and then output a forecast. What was happening was that this kind of pipeline was on fire for them, specifically, and then due to the operational nature of their role, they were also kind of time pressured and in a time crunch. So then my team came in, and what we found was, came in to help them, was that featurizing this data frame was where the biggest pains were, and this is where Hamilton started out. So just to peel back the onion a bit, so why was this data frame causing them fires? Well, it's a very wide data frame. So it's on the order of thousands of columns wide. It's on the order of tens of thousands of columns kind of rows deep. It's not big data, so it all fits in memory, but the main point is it's very wide. Why is it so wide? Well, columns just end up being functions of other columns, because that's how kind of featurization kind of works, especially when you're doing time series modeling. And what you get is this kind of successive chaining of columns being inputs to other columns, being inputs to other columns. And this is where this is what was causing them a lot of pain. Just to give you an example of like where did this pain come about? Well, here I have some sort of example code written in pandas that should be kind of familiar to you if you know pandas. But essentially what it's doing is, you're manipulating a single kind of data frame, and you're creating and adding columns to it. And as you'll notice that there's many different styles that you can do this in. And what I want to tell you that, if you're doing small things, this probably isn't a problem. But if you scale to like thousands of columns in a growing team, you're going to run into issues. So why is that? Well, one, if people can write functions or create columns in different ways, then there's a lot of heterogeneity in the code base, very different expectations depending on where you look. Inline data frame manipulations are great, but how do you test them? Code ordering becomes super important. So you can't really just arbitrarily change things. You kind of have to really know the order to really understand what's going on. And what this really means is that the testing and unit testing story is pretty abysmal. Documentation is also very difficult. Code reviews become slow and challenging because you really need to understand what's going on. And then therefore onboarding and debugging are actually challenges in this code base. In short, the code for featurization was causing the Fed team a lot of problems. So Hamilton. So what is Hamilton at a high level is, as a user, you write functions, Python functions. Hamilton, you give them to Hamilton. Hamilton creates a directed acyclic graph or a DAG that models kind of the data flow of computation. You then ask Hamilton, hey, give me certain sets of columns. Hamilton knows what to do, and then, for instance, can create a data frame just with those outputs. As I said in the beginning, Hamilton's a new paradigm, and what I mean by that is you write Python functions, but in a specific way, where the function name is an output column if you're creating a data frame, and where the function inputs then map to other input columns. And so on the right here, if you were to create a column C from some in column A and column B, you would have to rewrite it into Hamilton, where the name of the function, or name of the column becomes the name of the function, and the inputs become input parameters, and so they have to be named appropriately. We can make use of Python type hints to statically check things to make sure that functions line up, and then because it's a function, we can make use of documentation, the function documentation, to kind of document things. So how do we go from code to directed acyclic graph? Well, we kind of use the Python inspect module to crawl and find these functions. We pull the function names and parameters. Then it's just a simple case of graph theory 101 to create a DAG. To go from DAG to an output, we then you just need to provide what outputs you want. We then can walk the graph, figure out what inputs are needed, figure out the execution path. Functions are only executed once, and then they're combined at the end. So key point to remember is that with Hamilton, the function names and function parameters need to match if you really want to create a DAG. So for things to be stitched together, things really need to match. The second point to remember is with Hamilton, you don't actually have to maintain a pipeline. You don't specify at the end, like other systems, that, hey, I want to stitch these things together. With Hamilton, at the end, you just say, give me these outputs, and Hamilton does the rest for you. One sentence, if I was to describe Hamilton, is that it's a user-friendly data flow paradigm. As an aside, you might be wondering, why is it called Hamilton? Naming things is famously one of the hardest problems in computer science. And when we started this project, I was trying to go for associations with the Fed team. The Fed team reminds me of the Federal Reserve. What's something foundational about the Federal Reserve? Alexander Hamilton. And then it just so happens that, the Fed team at Stitch Fix models business mechanics, which has Hamiltonian concepts. And similarly, we're doing some graph theory stuff, which has, Hamiltonian concepts there. So I think Hamilton is a very appropriate name for this library. So let me show you some Hamilton code so you can get a better feel for what I'm talking about. So to use Hamilton, you essentially write Python functions, as I said before, and you stick them all into some sort of Python module. Here we're calling it myfunctions.py. The salient things to note is that the function names, if we want to create a data frame, represent the output columns that we want to request. And then it's very easy then to see what inputs each function require. And then also in this case, know that if we want to compute spend shift 3 weeks per sign up, we need to compute spend shift 3 weeks, which is this function here, and so forth. So how do you go get a data frame? Well, you just need to write some code, what we call some driver code. Let's walk through it. So first you need to set up provide some configuration, maybe some initial data. You then need to you need to import the Python module that you want to kind of crawl. You stick it together in a Hamilton driver, which creates the DAG. You specify what outputs you want, and then you execute, and boom, you have a data frame at the end. And then as bonus, you can also visualize things very easily. So if you want to know what the path of execution is, it's very easy to do so. So again, it is open source. You can go try it for yourself. I won't be offended if you drop off now to go play around with it. You should be up and running in 15 minutes. It's pretty easy to get started. So in short, what is Hamilton? It's a user-friendly data flow paradigm where users write functions that create a directed acyclic graph through function and parameter names. And then Hamilton handles execution of the DAG and creating outputs. So Hamilton at Stitch Fix. So after 2 years in production, it's been very successful for us, especially for the Fed team. So specifically, when we started out, the Fed team really wanted a code base where they could test things very easily. They had good documentation and a good development workflow. And by rewriting their code base into these kind of Hamilton functions, they got everything. And actually, I want to say we actually knocked it out of the park. So why was it a home run? Let's dig into that just a little bit. So say for testing and documentation, Hamilton forces this paradigm of you request outputs, and those outputs map to a single function. So therefore, there's a single place to find logic, and then therefore there's only a single function that needs to be tested to kind of check whether that output is doing what it's intended to be done. Yeah. And then the function signature actually makes providing inputs very easy. So creating unit tests is very easy. And then because of the way Hamilton operates, it forces function names and input parameters that mean something. So code should be pretty legible and readable to anyone. And then because we're using a function, you can reuse the function doc as a natural place for documentation. And so therefore, everything is naturally unit testable and everything is naturally documentation friendly. Hard to say that of many code bases. In terms of the workflow side, by writing these Hamilton functions, Hamilton also enabled the team to easily visualize computation, faster debug cycles, a better onboarding collaboration experience, and as a bonus, a central feature definition store. So from the visualization front, they have a data frame with 4,000 plus columns. How do you think about it? How do you visualize it? How do you explain to someone what's going on? Because we rewrite things into this Hamilton kind of way, it's very easy to visualize. So here I have a zoomed out view to obscure names on purpose, but the point is it's given no matter, it's very easy to visualize things and walk through them and explain to someone. And then you can also export. We create dot files so you can put it into your own visualization, another visualization system very easily as well. Debugging functions are super easy. Say we have a problem with spend shift 3 weeks per sign up, and we're trying to debug. We know that, hey, there's only one function that defines it, so we can go straight to the definition and look at it. If I didn't write this, it should be pretty understandable as to like what it's doing, because either the function name makes sense and there's documentation. And then it's very clear and easy to see what the inputs are to this function. So when I'm debugging, it's either the bug is definitively in this function or it's somewhere upstream. In which case, it's very easy to methodically, recursively walk back through the DAG and continue my debugging process. The nice thing about having these functions in a Python module is that you can also import them into other contexts and play around with them if that's also your style of debugging. Collaboration is also super easy when you're writing Hamilton style functions. Specifically, it means it's really easy to assess impact and changes when the names mean something. So the function names and function parameters are pretty understandable. When you're trying to add a new input, it means you're adding a new input to a function. Okay, you can assess the impact of the DAG. You can see whether that input exists or needs to be provided. If you want to change the names of things, it's very easy to assess whether you've changed everything completely, since it's generally just a matter of search and replace. If you're adding a brand new function, you're not going to break anyone else's functionality because it's going to be a brand new node in a DAG that is independent of everything else. And then similarly, if you're going to delete code, it's very easy to determine whether you can. Net result is that code reviews are much faster and it's easy to pick up where those left off, meaning that if someone leaves your team or you are handing off, generally because things are documentable and testable, it's very easy for other people to come in and pick up things. So the Feds team gained a central feature definition store as a byproduct of using Hamilton, and that's because Hamilton forces you to organize your functions into modules. The way that the Fed team kind of uses this is that they each function follows a team naming convention. So for instance, D underscore prefix to a function indicates that, hey, it's a date feature. So if you see it in any other context, that, oh, it's a date feature that's being requested. And then they organize it into thematic modules that better map their working style. So for instance, all date features are together in a single kind of module. And then this allows for them to kind of work on different parts of the DAG easily. And then because it's in a central repository, it's also versioned by Git. So it's very easy for the team to kind of create, find, and reuse features by the team. And then if you ever need to go back in time and debug something or recreate an output, it's very easy to do so since everything is versioned in Git. In case you don't believe me that the Fed team really likes using it, I got some testimonials. So first quote is from Danielle. The encapsulation, and she says this about Hamilton, the encapsulation of the logic in a single named function makes adding nodes, edges simple to understand, communicate, and transfer knowledge. So specifically in the context of, pull requests are easy to review and onboarding someone to the team is very easy. Another quote I have is from Shelly. She says, I like how easy breezy it is to add new nodes and edges to the DAG to support evolving business needs. So in their case, say marketing is coming up with a new campaign and they need to account for that in their modeling. So then they're adding a new feature for it. This takes minutes for them as opposed to hours before using Hamilton. So Hamilton and Stitch Fix, in short, like the impact that the Fed team had by rewriting things into Hamilton is that they gained naturally testable code, always, naturally documentable code, a data flow visualization for free, faster debug cycles, a better onboarding and collaboration experience with the bonus central feature definition store as a byproduct, and with a net result of a home run for them. I'm actually going to claim that by using Hamilton, the Fed team can continue to scale their code base, so go to 8,000 features or whatever, without impacting team productivity. Rhetorical question for you all: is that true of your feature code base? So hopefully by now I've kind of piqued your interest as to should I look at Hamilton? And I'm just going to go through some tips to get started. Specifically 5 things. So If you want to use Hamilton within your own ETL system, I want to say that Hamilton is compatible with any ETL system that can run Python 3.6. So Airflow, Metaflow, Dagster, Prefect, Kubeflow. If you can run Python 3.6 or above, you can run Hamilton. The recipe to do so is pretty simple. You just write your Hamilton functions, create some driver code to execute it. Then you need to make those Hamilton functions accessible in a way that you can run it in your ETL system. So either this means publishing it as a package, or checking, saving it to repositories for it to be checked out. You need to include SF Hamilton as a Python dependency, and then have your ETL system execute your driver code however you usually do that. And then that's all you need to do. Pretty simple. The other is if you're migrating to Hamilton. So what we did at Stitch Fix, the Fed team was a pretty big migration. So what we did there to kind of help with that was we created a continuous integration system to make it really easy and frequently to compare results as things were going along. This helped to kind of diagnose bugs as we were going along. And actually, most of the time, it was actually finding bugs in their old implementation, not the new one. So what we did, the kind of workflow was we wrote functions, checked them into Git. Then we had a CI system kick off a job, which actually computed the DAG and then also compared results with what was in production. And then it gave us a scorecard with which we could know, hey, we've correctly implemented this thing or not, and then made iterating and keeping tabs of things that much simpler. The second is if you want to integrate Hamilton into your workflow, you probably want to write a custom class to kind of match your existing API rather than trying to make your workflow match how to call Hamilton. And that's because when you're migrating, you want to kind of avoid making too many changes. So I think focusing on just Hamilton functions and in a specific way will make it easier. Specifically, what I mean by that is that with Hamilton, you'll define your functions, which will create a DAG. You'll then kind of instantiate a driver, which will then execute it. Now, rather than trying to get your existing inputs to match and run Hamilton directly, write this kind of wrapper class, which will can match to your existing API inputs and outputs so that it's much easier to kind of just insert Hamilton in and then worry about changing this after you've done your migration. In terms of key concepts to grok, the first is common index, especially if you're creating data frames as output. Hamilton relies on the pandas series index to join columns appropriately. And so at Stitch Fix, what this means, the best practice was when you load data, you essentially want to ensure that data that's loaded has a common kind of spine or index that makes joining kind of just work as intended. And then from there, you can kind of continue with your normal transformations. Because the Fed team does time series modeling, what this meant was that each data input had to have a common date time index. The second is naming. So function naming, as I've kind of harked on, is pretty important with Hamilton. It helps you create your DAG. It drives collaboration and reuse, and then it serves as documentation itself. Key thought is you don't need to overthink it, so you don't need to get it right the first time, because it's really easy to search and replace, especially if you're writing things in a central repository. It's really easy to search and replace and change things as your thinking evolves. But it's something that you should converge thinking on, since that does help drive collaboration and how your team functions. The third is output immutability. So because functions are only called once, it means that you can generally kind of come up with a pattern where what it outputs is immutable. Now, that's only true if you don't mutate that output in another function. Specifically, say if you are operating over a pandas series and you get passed in one, don't mutate it, create a new one. Otherwise, your mileage may vary when you're debugging. So best practice here is to test for this in your unit tests if this is important. Otherwise, clearly document that you're mutating inputs so it's easier for someone who comes across things to understand what's going on. Fourth thing is code organization Python modules. So functions are grouped into modules, and then use modules as input to create a DAG. Use this to your development advantage. So use modules to model team thinking. So in the case of the Fed team, they stuck things into modules that made sense for them. This helps isolate what you're working on and enables you to replace parts of your DAG easily for different contexts. Specifically, when you create a driver, you pass in a bunch of Python modules. You can kind of not include modules to change the shape of the DAG and what's available. You can easily kind of create shadow modules to replace things. So it's if you get the module structure right, it gives you a lot of kind of ability to kind of compose and change the DAG as necessary. Fifth is function modifiers, or also known as decorators. So what do I mean by that? You might see a Python function with an add above it. Hamilton has a bunch of these to modify behavior. So an example here is if you're loading data, typically say you're reading from a CSV, it comes back as a data frame. Hamilton works best by thinking in columns. So we have a kind of, a decorator here that you could provide that will say extract the columns of the data frame for easier downstream use. So best practice here is to learn to use them, because they do improve and increase functionality of Hamilton, and they also help to keep your code dry. And the Feds team's favorite, for just in case you want to know, is @config when. Okay, so last 5 minutes or so, I'm going to talk about extensions. So why talk extension at all? Well, the initial shortcomings to Hamilton were that it's single-threaded, so it didn't run kind of in parallel in any way, and it could not scale to big data because it was only could run on things that were in memory. You can only produce pandas data frames, and it didn't really leverage all the richness of the metadata that we got when we created this DAG. So I'm going to talk about some recent work we did to kind of remove some of those constraints, and then talk about some future ideas that we're interested in exploring. So the first is scaling computation. So Hamilton grew up with a single core and memory limitation, and this was a blocker to adoption for some. But our goal in kind of providing this capability was to not modify Hamilton code at all to scale. So if you're creating, say, a pandas data frame, things should just work. That's kind of the idea. What I mean by that is this code that I showed you before, we don't want you to have to change this code much at all to be able to kind of scale to bigger data sets and data sizes. Luckily for us, Hamilton functions are generally very amenable for distributed computation, because they define, because everything's encapsulated in a function, we can distribute those functions pretty easily. And then just so happens, Pandas has a lot of support for scaling these days out of the box with various different systems. So with the 1.3.0 release that kind of we just put out, you gain experimental versions of running Hamilton on Dask, koalas on Spark, and Ray. And so the short of it is you can scale pandas out of the box right now. Why are they experimental? Well, they haven't been baked in production for long, so hence just a bit of a caveat that, like, hey, this still isn't fully baked yet, but it does mean that you can kind of scale things very easily. Just to kind of give you an example of, like, well, just how easy should it be? The only code you should really have to modify is the driver script. So here, you might have to just change how you load data into the system, just because, if you're using Dask, you want to kind of load it in a distributed manner, how Dask would like you to. You then have to instantiate a client, say for Dask or for Ray, or Spark context. We introduce a concept of a graph adapter. You instantiate one, you pass that into the driver constructor. Then as normal, you kind of request your outputs and execute, and that's so basically 4 lines of code to scale. I think is pretty cool. So custom return objects. As I said before, Hamilton grew up, building pandas data frames. That's all it used to be able to produce. What if you don't want that? Well, in the 1.3.0 release, you now have control over what the final object can be. So for instance, if you want to return just a dictionary of outputs to some sort of object, you can return an NumPy matrix if you're doing NumPy things, right? Or custom objects, or even TensorFlow, PyTorch things, you name it, you now have control over it. Again, it should be pretty easy to use, and so you just need to modify your driver. Again, you kind of have to instantiate a graph adapter. A graph adapter can kind of take in something that kind of tells you how Hamilton should kind of create this result. Again, you pass it as a constructor, and then here I'm actually requesting, hey, give me a dictionary of outputs, and then when you call execute, you now get a dictionary of outputs, not a data frame. Row-based execution. So what if you can't fit everything into memory, or you want to reuse your graph and call execute within a for loop with different inputs? Before, you couldn't do that with Hamilton, or it was kind of awkward to do so. So in this 1.3.0 release, it enables you to configure a DAG once and then call execute with different inputs. So this enables you to, for instance, to chunk over data, or you reuse the same DAG but pass in different inputs, and potentially opens up new use cases like image processing or NLP for being modeled within Hamilton. Again, just to show you, like, the only thing that changes here is the driver script or the driver code. You instantiate your driver, and actually to chunk over things, we now kind of expose an inputs option when you execute. So here you could load a data set, put it in a for loop, and then get different outputs depending on the input. So in short, as of the 1.3.0 release, Hamilton now scales for distributed and parallel execution with experimental versions of Dask, Koalas, and Ray. And it becomes a general purpose framework since you can return any object type now, NumPy, PyTorch, dictionaries, you name it. And we also enabled row-based execution. So this gives you another a way to kind of chunk over data sets or process things like images or text. In terms of planned work, in no particular order, we're kind of thinking about, say, number integration. Can we include some notion of data quality when you're defining a Hamilton DAG, and lineage surfacing tools? So what is number? For those who don't know, it's a way to kind of compile Python code to machine code or compile it to GPU code. And a task here would really to be, can we wrap these Hamilton functions and compile them for speedy graph execution? This means that if you're doing NumPy work, you should be able to get, according to number, very, very good performance gains. Data quality. So with Hamilton, we can do runtime inspection of outputs. Can we incorporate some of these expectations like Pandera? So Pandera is an open source kind of framework for doing so. Here I have a kind of a mock API example, but say you have some important output that you want to kind of check for. Maybe there's a way that you can tell Hamilton like, hey, when you run this, check the output and like here are my expectations. So we're looking to how can we kind of include that into the Hamilton framework? The other is lineage surfacing tools. So say you want to ask things of the metadata we have. The task here is like figure out ways of, what are good ways to expose information. You might be interested in this if you, have PII or GDPR and you need to kind of understand your exposure or where things are used. I mean, because with Hamilton, we kind of have, column level information of like how data is used in a data flow. So can we expose that? Can we help people answer those questions? Similarly, if you're developing with Hamilton, maybe there's a way that we can leverage it to tell you like, hey, if you change this, these are the downstream impacts. And then because we know that, hey, if things are checked into Git, maybe we also know potentially who you should talk to kind of notify or if you want to make changes to a DAG. If you're excited by any of these extensions, do go and like thumbs up, love them, because this will help, figure out where potentially we should prioritize our time. So in short, to conclude, Hamilton is a new paradigm to describe data flows. It grew out the need to tame a feature code base at Stitch Fix. And we believe, or at least I believe, the Hamilton paradigm, provides teams with multiple productivity improvements and can scale with code bases without a loss of productivity. And with the 1.3.0 release, it's now a scalable general purpose framework. Thanks for listening. Would love your feedback. Pip and Stoice have Hamilton, star the repo, create issues, vote on issues on GitHub. And then if you want to join us on Discord, we're curating a community there and would love to have you. Thanks. Happy to take questions.
So I'll read
a lot of information.
That some people were putting in the chat, like, I didn't realize I put it on 2x.
Oh,
right now.
I'm sorry for the people on YouTube who wanted to come back and watch it at 2x.
Yeah, exactly. You're just going to hear. Anyway, there's some awesome questions that came through. One, actually, there was a good discussion going on around like how lightweight Hamilton is. And so that's something cool that's happening. But then there's one that just I should probably bring up because we are talking about feature stores so much. And does Hamilton work with feature stores like Feast or Tecton?
Yeah, so Hamilton doesn't tell you where you should materialize or store your data. So you could use Hamilton as a way to compute things, and then it's up to you to push it to, Tecton, Feast, you name it. Like Hamilton isn't opinionated as to like what the actual store is. It's just a way for you to kind of define the computation that you want to happen to create a feature. Nice.
And this is a really cool question too. So Javier is asking, so Hamilton connects with Dask. In my view, they perform a similar task. What are the differences there?
I mean, it's just mainly the API, right? So like with Hamilton, you're writing these things in this Hamilton function. And so you kind of define your data flow graph by writing these functions, in which case with Dask, you would have to kind of annotate and do all that manually. You would have to basically have like the pipeline step that would say, hey, take this input, put it into this function. But with Hamilton, we can do that for you.
Oh, nice. All right. And then this is another great one. How does Hamilton handle duplication, i.e. creating the same data with different names?
Those right now get created fine. It's Hamilton does catch the case if you have multiple functions defined and you're trying to create a DAG with them, but it right now doesn't have any capability to catch that case. If you name functions, if you're creating the same output but named with different functions, Hamilton doesn't currently catch that.
So the other thing that I will mention to everyone, if you have not seen it, there's a great blog post on Hamilton when you guys open sourced it. It's really informative and it helps. There's a lot of people that looks like they want to go test it out and have a play with Hamilton. So hopefully that works. Go see the Discord community and say hi to Stefan. Thanks, man. This was cool.
Thanks for having me, Demetrius.